Problems involving complex summation technique II. So I have already done two problems in this series, introduction and problem I. So I think by now you should have known what is really complex summation technique. So this is basically just taking cos and sine in terms of e to the power I theta and writing them as a real part or imaginary part, and using the fact that real part of function times a real number is all again use just the real part here, and again that is linear. So these properties will help us to solve the sums. Yeah. So let's do it. So sum from, okay, let me change to black. Sum from n equals to 0 to infinity of 4 to the power minus n. This is just the real part of e to the power I theta. Yeah, e to the power n theta is I n pi by 3. Yes. Now take this to all this inside and then outside the sum. So we have the real part of sum from n equals to 0 to infinity 4 to the power minus n e to the power I times n pi by 3. Yes. Now the real part of, now let us write this as an infinite geometric sum. Yes. And we get e to the power I pi by 3 by 4 to the power n. Now we know that the modulus of e to the power I pi by 3 by 4 is just 1 by 4, because the modulus of e to the power I pi by 3 is just 1. Yeah, so since its modulus is 1 by 4, which is less than 1, we can use infinite geometric series formula. That gives us the real part of the formula is a by 1 minus r. A is just 1 because power 0 is 1. A by 1 minus r is just e to the power I pi by 3 by 4. Yes. Now this is the sum. Now let us take 4 to the numerator. Over here 4 minus e to the power I pi by 3. Yes. Now we can basically either just expand this and then rationalize the denominator just so as to just have the real numbers in the denominator, and then find the real part from numerator. Yeah, you can do that. Yes, that is a possible option, but the other option, just to make the denominator real number, is also to multiply this by the same number but with a conjugate over here. That is to multiply by 4 minus e to the power minus I pi by 3. Yes. And if we do that, what we have is basically 4 minus e to the power minus I pi by 3. Now that will be real part of the 16 minus 4 e to the power minus I pi by 3 by, now this is 16 minus 4, yeah, e to the power minus I pi by 3, and then again plus e to the power I pi by 3, and then just plus 1. Yes. Now I see that we know that this sum is actually just 2 cos theta. Yeah. So now all of this is just real number in denominator. The real part of the 16 minus 4 e to the power minus I pi by 3 by 17 minus 8 cos pi by 3. Yes, 8 cos pi by 3. Okay. Now if you have to find the real part, just to find the real part in numerator, and that gives us 16 minus 4 cos pi by 3. Yes, and then over in denominator we have 17 minus 8 cos pi by 3. So now this is gonna be the answer. Cos of pi by 3 is just 1 by 2. So basically 16 minus 2 by 17 minus 4 is the answer. That is 14 by 13. So let's check if 14 by 13 is the answer. Yes. So this is the answer, and this is a pretty neat answer. Yeah. So basically the sum that we had to do involved some cosines and exponentials, yeah, and this thing, and it's going up to infinity. Literally, cosine functions going up to infinity. You might like never really be able to predict that the answer is just a simple rational fraction. Yeah, That's quite unpredictable that it can be a normal fraction for method. But yeah, this is it. And the complex summation technique really helps us see through it and solve this problem. So this was a nice problem where complex summation was really helpful. Hope you enjoyed the video. Thanks for watching and look forward to seeing you in the upcoming videos too.